So welcome to the stage Klaus Mühlhans, who's got 37 years of experience in organising and optimising the flat glass processing. So without further ado, I'll hand it over to you, Klaus.
Thank you. So, thank you all for being here. I'd like to give you a presentation on organization of a shop floor in a glass processing plant and what to do to keep your growth sustainable, because there's problems when you grow that rise and rise and rise, and clearly you want to have, if possible, linear growth, and that is only possible if you have a good organization, and I'm going to present you some ingredients to do so. And to go along, one important point that we have to discuss and keep in mind that is a problem for everyone running such a factory is the lot size conflict. I'm going to explain to you this lot size conflict because it's essential to understand what we are going then to do to resolve that conflict and to find a way out. This lot size conflict conflicts very much with just-in-time planning. Therefore, I will need to spend a moment to give you an insight how these things influence each other, and clearly a summary at the end. So, where are we at the beginning? The lot size conflict. What is this about? I have a little picture where it's already obvious, but I like the picture, that's why I put it in here. There's always a conflict. There is this seesaw, and for example, boss orders and yield is a conflict that everybody knows, and that's why I wanted to put it at front here. Yeah, you cannot get a good yield when someone is influencing always your production. This is just one example. There are a lot more. And we're coming to a bit deeper into it. This is the reality you have in daily production. The best way to organize your production is to be dispatch-oriented. So you want to have everything in that area. You want to cope with boss orders because they are natural. You cannot avoid them. You need quick replacement. You all know glass is a brittle product. It gets broken, you need a way to complete your orders, otherwise just-in-time delivery is impossible. So all this is on the left-hand side of that seesaw. On the other hand, you want to have your production yield-oriented, you want to have high productivity, and to cope with that, you need large quantities, and you need to stick to the planning. And this balance between these two, that's something that every production manager you talk to, he will feel in his heart that he has to solve that every day. I'll give you some examples, digging a bit deeper into the story. Here we have, for example, the cutting area where it's easy to see and most prominent. This shows you racks where after cutting you have to place the glass. If you want to have all these sheets in dispatch sequence, you want to be easier in the rest of your production. That conflicts very much with the cutting yield, because then you do not have a chance anymore to do an optimization in a chaotic way. So, again, this conflict. This type of conflict here that you have in cutting, there are already some solutions to solve it, but I come to the fact that this is only a partial solution in a minute. You see, here, there's one way to do it, because if you want to be chaotic, you have to sort. You may use half breaks, you may use sorting systems. This is an ease of that situation, but it's only one part of the story in the beginning where you feel it. There are other areas in production where you have exactly the same conflict and where you have to address also solutions. The main part why we get this conflict is due to the way how we do the planning and how we organize our production. This is something we have to keep in mind, and that's why it's important to spend a moment thinking about the principles we use to plan our production and to actually schedule what we do there. Today's state-of-the-art knowledge is using just-in-time principles. I think you all know more or less what it means. So the typical workflow today would be you're receiving your orders in your order processing system that you have, which is state-of-the-art. These orders are analyzed, and we are talking about, for those not being every day in a flat glass processing company, we are talking about a variant production where every single piece is different. So all these pieces have to be analyzed, they have to be organized, they have to be assigned to respective production processes, and for each process the quantities have to be accumulated. Then things come into account like capacity limits, that you cannot do an infinite number on a furnace, for example. You have to obey certain rules. And doing all these planning steps, in the end, results in the last point in time when something can get started. So you know it has to be at 10 o'clock at the everything line, it has to be at 12 o'clock latest at the furnace, to be at 4 o'clock in the afternoon in the dispatch area to be shipped to your customer, something like that. This is what just-in-time planning is doing. What do you get as a result? As a result, you get certain quantities you have to do within a shift. And every single sheet within that shift gets assigned a production unit, a shift, a point in time when it has to be started. So that's all understood, well understood practice done every day. So what results out of that? Someone is sitting there, after these automatisms that have been done inside the software, someone is now sitting there looking at the results there, at these quantities and the planning, and is doing a manual scheduling process now for the actual production, knowing what is to be done when. So he's using software to group batches, which to do when, and now he is also facing the lot size conflict, because the idea is, do I take 100 units into a batch to optimize them together? Do I take 150 or only 50, depending on the needs every day? And is it better to have 50 on the everything unit or not, or maybe 100 or whatever? That all conflicts, and this is done manually at the start of production, and then it is fixed. And that means whenever you change it later, it gets complex. In many, many companies, it's already the case that at that planning at that stage, paperwork is printed, labels are printed, so it's very cumbersome to change anything afterwards. You have to stick to that. Yeah. So whatever changes come, breakages and so on, everything is cumbersome and disturbing that, reducing your yield, getting less productivity. And also the additional products, like additional items, like for example frames, spacers, things like that, that all requires a manual organization to fit to the production process. When something goes wrong, you have these people running around with a glass sheet following, so that at the end it gets together. Some more areas where you have this visible, how deep that conflict is. Here, these are measured examples. The theoretical maximum in cutting, when you have chaotic optimization and enough to combine, you can reach up to 98% cutting yield. But when you look into a flat glass producing plant, the real yield that they achieve at the end of the month when they have their balance there, and look what they earned, the real one is float glass between 10 and 20% loss, and for laminate glass even up to 25. This, between the 98 that you could theoretically reach, this difference is the lot size conflict and the influencing things in the factory. So something has to be done about that. One more prominent thing that also influences that, for example, when you have smaller quantities, you get residues. And these are measured figures here. I took figures from a typical glass producing plant. The optimization yield was in the area of the 90s, which looks quite well. But there were residues. And if you assume that the residues are all thrown into the bin, the real yield of the factory would be in the area of 70-something. So you say you use some of the residues, okay, but the realistic curve is here. You see how much difference it is. And keep in mind, 1% yield is a hell lot of money. Yeah, it's typically still in the age of a salary of a typical worker. So something has to be done. And on the shop floor itself, what do we do? As I said, the orders are coming in, they are all just-in-time planned. The scheduler takes it and it does his work. And then everything is pushed through. Yeah? So even so the planning was done in that direction, the production organization now is going forward, which is in contrast to the planning. We all do that. Yeah? So they all get their paperwork, and then the processes start until shipment. So this is today's practice. And I think it's difficult to get out there because this can be done by humans as well as by software. It's something that is understandable, that is under control. If we want to get out of that, it is difficult, but there is a way out. And this is what I want to show you, that there is a way out to get there. Because wouldn't it be nice if we can break this seesaw? Yeah, if a customer order has no impact anymore, if breakages have no impact anymore, or the least possible amount of impact or whatever, boss orders, all this has no impact anymore, but the system keeps that under control by itself. And that is something we aim now, and that is something that is possible. We are already partially there, and we will get there totally in the near future. And that is by using a software that is running the shop floor control as well in a pulling mode. Meaning that the detailed control of the processes in the production are controlled in the same way as the planning before, meaning from the end. That means whatever is here influences just in time everything else before. How is that possible? That is possible with a new level and a new generation of software where we have a second level, so to say, an artificial level on top, like a digital twin. For each process, we have a software agent. And each of these software agents are communicating between each other like before humans did. The quantities determined by just-in-time planning, every single sheet having a timestamp when it is needed and in what sequence is needed. These quantities are continuously exchanged between these software agents so that they know what's happening in what area. If there is a change, it has an immediate effect because they communicate immediately with each other. This is basically the idea. The consequence, for example, you are at the furnace. The furnace is now idle because the next furnace bed is free and you can load it. Then this agent here, talking with the other agent, can determine at that moment in time what would be the best quantity to run as the next batch in the furnace. And as this is done just in time, the moment the furnace bed is loaded, it can take into account any changes that happened here later. So it's really working in a backward organized mode. This is the core idea of this pulling principle, just to organize everything from the end. Meaning that, for example, then the cutting area, at the moment when the next jumbo sheet arrives at the cutting table, that is the moment when the system determined what fits best on that plate. So there's no batching nor computation hours before. The computation, what is on that plate, is done in the minute when the plate arrives in the cutting table. And with this, you get the utmost flexibility because it takes into account everything known so far, all the changes, the breakages, even the breakages here under, they will have an influence. So we have to think backwards. This requires a complete new generation of software because the existing software cannot do with this. And it requires a rethinking and also a reorganization of the shop floor. It's a breaking change, not easy, but we can do it step by step, fortunately. We have it under control already, fully under control for the cutting area with one process after the cutting area. There we are running fully in a backward pulling mode. For the next steps, that is now soon coming. And then the aim is to have this full backward control. So where we are at the moment, we have a scalable product solution because due to these agents which are running as software agents which can run once or 100 times, because today's software is organized in services, today's software can cope with that. There is no limit anymore in that case. So this is available, and this is already supporting several sorters and AREX and things like that. So this is there. And for the future, it will even go further in the sense that this planning part in the office can be done automatically, because today there is still a planner that is influencing the processes, but it will be that there is just a guy that is supervising the whole flow, but the software itself will be reactive and see what it can do. So in summary, because I think that's about it, or the time, yeah, roughly. But when you, 5 minutes, including discussion, I think. So, when you remember what I said in the beginning, this lot size conflict and the conflict between the just-in-time planning and the push-oriented shop floor organization. When you want to grow, these problems that this conflict makes, they get larger and larger and larger. So the only way to get really sustainable growth is to solve that problem. And that means in the future, we definitely have to go to an organization which is based on pulling principles. Other industry segments do that already, but you have to remember, when you work, for example, with the Kanban principle, then it's easy to have a pulling part, because what you pull is a standard pre-product, which you then produce another 10 times. Here we have an industry where every piece is different. So that means to get a pulling principle run means you need software agents that communicate the individuality of every single piece through the chain with each other. Otherwise, it's not possible. That's why only with a new generation of software this can be achieved. And then any influencing factor during production can be instantly taken into account, and this breaking change can appear in the factory. Okay, that's what I wanted to show you, to give you a glance on what the future has ahead of us. I think it's really it's a challenge, but it's a good challenge, and I think it will be a big change, a positive change. And thank you.